To find the area of a region with polar curves, let's use the formula A equals the integral from A to B of 1/2 r squared d theta. In our first example, we have r equals the square root of 2 theta, and we want theta to be between 0 and pi halves. We know that that's probably going to be a spiral. We don't actually need to see the graph, but if we wanted to, we could throw it in the calculator and see what it looks like. And it looks like we are looking at the region from 0 to pi halves, which is going to be this shaded region here. So our area is going to be the integral from 0 to pi halves, 1/2 r in this case is the square root of 2 theta. We want to square r d theta. Now let's simplify what we have. Squaring the square root will make the radical go away, so we're left with 2 theta. 2 times 1/2 is just 1, so that leaves us with the integral from 0 to pi halves of theta d theta. Now we can integrate. That will give us 1/2 theta squared, and we are evaluating from 0 to pi halves. We can now plug in those limits of integration. We have 1/2 pi halves squared, and when we plug in 0, that's just going to give us 0, so we don't need to actually show that. We end up with pi squared divided by 8, and this is the area of that shaded region. In the next example, we're given the curve and we are given the shaded region, but we're not given the limits of integration. So we have to recognize that we are integrating from this angle pi halves to the angle pi. And once again, the formula for the area is the integral from A to B 1/2 r squared d theta. Let's just plug in what we know. We have the integral from pi halves to pi 1/2 times r, which we are told is 2 plus cosine theta. We want to square r and then d theta. Let's go through and square that binomial. We'll have the integral from pi halves to pi 1/2 times 4 plus 4 cosine theta plus cosine squared theta d theta. Next, recognize that we don't have an easy way to integrate cosine squared theta. So let's do a little bit of work off to the side and recall one of those trig identities. Cosine of 2 theta is 2 cosine squared theta minus 1. Now we'll use a little bit of algebra here to isolate the cosine squared. We can add 1 to both sides. And then divide by 2. And we now have cosine squared theta. So we're going to replace this piece here with this statement, because we know we can take the integral of cosine of 2 theta. So once again, we're just going to rewrite what we have. Pi halves to pi 1/2 times 4 plus 4 cosine theta. Replace cosine squared with this piece 1/2 times 1 plus cosine of 2 theta, and all of that is times d theta. Now we can go through and distribute that 1/2 on the inside. We have pi halves to pi. Just copying this first bit. 4 plus 4 cosine theta. Now we'll distribute the 1/2. That's plus 1/2 plus 1/2 cosine of 2 theta and d theta. Next, we'll do a couple things. Let's see if we can clean up the inside a little bit. We have some like terms with the 4 and the 1/2, and then we'll also distribute the 1/2. That's going to give us, let's see, that'll be 9/4. Continuing to distribute the 1/2, we get 2 cosine theta plus 1/4 cosine of 2 theta and d theta. Now let's actually integrate. We'll get 9/4 theta plus 2 sine theta plus 1/8 sine of 2 theta. We are having to do some u sub kind of in our heads here to integrate the cosine 2 theta. And limits of integration there, again, pi halves to pi. Now we'll plug in those limits of integration. 9/4 times pi plus 2 sine pi plus 1/8 times the sine of 2 pi. Then we need to subtract, plug in the lower limit. 9/4 times pi halves plus 2 sine of pi halves plus 1/8 sine of 2 times pi halves. And now we have 9 pi fourths. Sine of pi is 0, so we can think of that as plus 0. Sine of 2 pi is, again, 0 minus, then over here we get 9 pi eighths. Sine of pi halves is 1, so 2 times 1 is 2. Sine of pi is 0. So simplifying this, we get 9 pi eighths minus 2. And once again, this is the area of that shaded region.